Hello everyone for today's contributed talk sessions. So today we have Alberto Dayan from Norwegian University of Science and Technology, and he will be talking about weakly separated bessel systems of model spaces. So please.
Thank you. And well, let me start by thanking the organizers for putting up such a great series of conferences and courses. I think it was it is a really great program, and it's a really, good to have such a chance to gather, even, given the times. And thank you very much for giving me a chance to be here and talk today. So today I would like to talk about model spaces, and in particular separation of model spaces. And I would like to show that if you are in the hard disk page and you get a sequence of model spaces, that there are a bessel system and they're weakly separated, therefore they are resistant. I'm going to define all those notions during this talk. And we'll show how this has some relation with some more generalized interpolation problems. Okay, so it's not going down. Okay, it is. Let's start from the basics. So if we have a sequence in any Hilbert space, then such sequence will be a bessel system if basically the norm in the hard space of any linear combination is bounded above by a constant times the L2 norm of the coefficients, whereas it's a risk system if this norm is comparable to the L2 norm of the coefficients. And we have been talking about those in the course, of course, in this first day. But moreover, you can extend those notions of bessel system and risk system to subspaces or to sequences of closed subspaces of any Hilbert space. And you do that by asking that no matter how you choose a sequence of unit vector xn in the Hilbert space, such that each vector xn belongs to one different closed subspace hn, then this is a risk system, and the risk bound, so the least C for which this set of inequality holds, doesn't depend on the sequence xn that you choose. So it's kind of a uniform risk system condition, whereby uniform means that it holds uniformly on the sequence that you choose. Okay, so for us in this talk, at least, H will be the hard space. So the set of whole holomorphic function on the unit disk with square summable Taylor coefficients. And well, it is well known that this is a reproducing kernel Hilbert space, namely point evaluation and each point of the unit disk is a bounded linear operator, and therefore by race representation theorem, we have a kernel, namely there exists for any W in the unit disk, there exists a Zigo kernel SW that represents evaluation of a function at W through the inner product of H2. And so H infinity, the set of bounded analytic functions on the unit disk, can be seen as the multiplier algebra of H2, namely of the set of all holomorphic functions on the unit disk that multiplies H2 into itself. And actually the sup norm, the H infinity norm of a function in H infinity coincides exactly with the operator norm of the multiplication operator by phi. So M phi is the map, the linear map on H2 that sends F to phi times F. And the norm of such operator is exactly the sup norm of phi. Well, it turns out that such the fact that H infinity can be related to reproducing kernel Hilbert space, it helps to understand interpolating sequences on the unit disk for H infinity, where an interpolating sequence on the unit disk is just a sequence such that for any sequence of bounded targets, Wn, you can find a function in H infinity, phi, that sends each lambda n to each Wn. Now, intuitively, this is a separation condition of the lambda n's, because you want to be able to send the points of the sequence lambda to any possible target. So they have to be well separated because you need to specify the value of the n plus first, no matter what the other values are. And to see that from an operator theoretical viewpoint, well, one can prove that in any reproducing kernel Hilbert space, not only in H2, but in particular here, if you have the kernel functions are eigenfunctions of any adjoint of a multiplication operator by functions in the multiplier. So in this case, H infinity. And so asking that there exists a function with a small H infinity norm that interpolates those values is the same as asking that there exists an operator M phi star, which is bounded, so has a small norm in the operator norm, which has those kernel functions as their eigenfunctions with some eigenvalues. And so namely, a separation condition in the unit disk becomes a separation condition for those kernel functions, for the kernel functions of the points of the sequence. And actually, this can be made, of course, more precise. And Shapiro and Shields proved that in 61 that sequence lambda is interpolating in the unit disk for H infinity if and only if the sequence of normalized kernels. So when I write those hat here, it means that I'm normalizing the vectors in the Hilbert space. The sequence of normalized kernels at the points of the sequence is a RIS system. And then Carlson in 62 showed that characterized interpolating sequences in terms of Carlson measures. And it turns out that the Carlson measure condition can be translated in this language by saying that the sequence of normalized kernel at the points of the sequence is a bessel system, according to the definition that we saw before. And plus weak separation condition. So here I'm asking that basically the angle between any pairs of these distinct kernels at the points of the sequence is uniformly bounded below. And actually, this can be extended, so it's true not only in the Hardy space, but in all the reproducing kernel Hilbert space with a complete peak property. And one way to see that's actually pretty recent, I think it's 2018, Halleman, Hartz, McCarthy, and Richter showed that the equivalence between 3 and 2 can be derived by the positive answer of the Feichtinger Conjecture, which was solved by Markus Spielmann and Srivastava in 2011. That basically says that in any Hilbert space, a bessel system can be partitioned into finally many RIS systems. So basically what they show is that if your reproducing kernel Hilbert space has the peak property, then using this theorem, basically, if you have a weakly separated bessel system of kernels, that's actually a RIS system. And so the goal, so part of my thesis work actually, was to extend this theorem, the theorem of Shapiro and Shields and Carlson, to sequences of more complicated elements from an algebraic viewpoint. So in my case, in our case, sequences of matrices, where in order to define what an interpolating sequences of matrices, of square matrices is, well, of course, you need to specify what it means to apply a holomorphic function to a matrix, but that's just via the functional calculus. So you basically extend Cauchy integral formula in this way. And well, for this inverse to make sense, you're going to have to require that the spectrum, so the eigenvalue of each of these matrices, is inside the unit disk. And here, I'm not going to ask anything regarding the dimensions of those square matrices. So the first one may be 7 by 7. The second one can be 100 times 100, and so on. So there is no like bound on the sizes of the dimensions of those matrices. And so, well, when we started, as far as we knew, there was not a definition even of an interpolating sequence of matrices. So the first thing that we had to do was to come out with one. And one, I think, pretty standard attempt will be the following. So you take any bounded target sequence, Wn, which is a sequence of matrices with matching dimensions of the ones of the ANs, and you ask that they are bounded in the operator norm. And you define AN to be interpolating if for any such a target there exists an H infinity function that sends the AN to the Wn according to this integral formula here. But this turns out pretty soon to be not to be the right definition, because, for example, if you start with a sequence, an interpolating sequence of scalars in the unit disk, then you construct those sequence of 2 by 2 diagonal matrices, so lambda n times that entity. And well, you want that to be interpolating to a certain sense. And so, but you suddenly realize that if you take Wn to be constant, even, so this non-trivial Jordan block, 2 by 2 Jordan block, well, there is no function phi that sends A1 even to W1, because, well, phi of a diagonal matrix would be diagonal. So the problem seems to be that holomorphic function preserves invariance of spaces of matrices. So the fact that those are not points, but more complicated objects from an algebraic viewpoint seems to kind of make the definition a little bit less trivial, at least. So even a one-point interpolation problem under this definition will not work. So the way we overcame this problem was just to identify a bounded targets with a bounded sequence in H infinity. And so we say that the sequence AN of matrices is interpolating if for any bounded sequence Pn in H infinity, there exists one function in H infinity that does the interpolation job, so that agrees with Pn at each AN. And so with this definition in mind, we try to extend Carlson interpolation theorem to those sequences of interpolating matrices. And we'll see that we will use those model spaces and those separation condition of model spaces to do that. Because, well, the first thing that we had to do was to find a replacement for a kernel, because when you have scalars, then you can use separation of the kernel functions in H2 and you get some interpolation properties. So here, what should kernels be when you're starting with a sequence of matrices? And it turns out that the answer is the following. So you define Hn for any given your sequence AN of matrices to be the orthogonal complement in H2 of all the functions in H2 that vanishes at AN. And observe that thanks to the reproducing property, basically, if AN is just 1 by 1, so it's just a scalar, lambda n in the unit disk, that Hn is precisely the line spanned by the kernel functions at lambda n. So it kind of works as an extension in that sense. Well, if also Pn is the minimal polynomial of AN, then any other polynomial that vanishes at AN has to be a multiple of Pn. And it turns out that if you start with a polynomial and you do Pn of z over this Schwarz reflection across the unit circle, you always obtain inner function, where by inner function, I mean a function in H infinity whose radial limit is almost everywhere on the unit circle unimodular constant, so has modulus 1 on the unit circle. And so thanks to the factorization theorem in H2, you get that, well, a function in H2 vanishes at AN, if and only if it's a multiple of this Pn, that we'll see in a bit, it's just a Blaschke product, actually. And so our space Hn that we described above is nothing but a model space. So it's the orthogonal complement in H2 of all the multiples in H2 of an inner function. And this helps a lot because lots of people studied model spaces. There was a section in this series of seminars on model spaces. So it's a very well-studied object. And so that helps to understand how to separate those, how to find equivalent condition in order to have separated model spaces in a certain sense. But before getting to the main result, let me just give you an example. So suppose that A1 is this. So it's in this Jordan canonical form is just this matrix. And the fact that this A1 is in this Jordan canonical form, it doesn't take away any generality, because you can always, so each matrix in the sequence is similar to a matrix in its Jordan canonical form. And since holomorphic function preserves similarity without loss of generality, we can assume that all the matrices in our sequence of matrices are in their Jordan canonical form. Well, if you apply a holomorphic function to such a matrix, you get, well, on the diagonal, the F at the eigenvalues. And if you happen to have a Jordan block, which is not, which is larger than 2, let's say, you also pick up some derivative of the function. And so that means that a function vanishes at A1 if and only if it vanishes at their eigenvalues at f prime of lambda is also 0. And so the inner function that kind of define the model space H1 is precisely just this, because you have a multiplicity 2 at the eigenvalue lambda and multiplicity 1 at the eigenvalues gamma in this case. And in particular, that means that you can actually write a basis of this model space, which is just the linear span of the kernel at lambda. So the kernels at the eigenvalues plus some kernel that represents derivative, the value of derivatives at the eigenvalues in H2. Because here you had this 2 by 2 Jordan, non-trivial Jordan block. And so you also pick this S1 lambda. So that's the idea. Each one of those HNs is just span of some kernels in H2. And so the theorem that extends the one that we saw before at the beginning of this talk is the following. So a sequence A of square matrices with spectra in the unit disk is interpolating if and only if the sequence HN that we defined before is a RISC system in the more general sense that we saw in the first slide. And that's equivalent to asking that HN is a bessel system, which is weakly separated. Now, by weakly separated, that means that if you take any two distinct of those model spaces, HN and Sj, their distance, namely the least distance between two vectors in H and Hj, respectively, is uniformly bounded below. And this, of course, if An are scalars, all those Hn are one-dimensional, and that is exactly Carlson's interpolation theorem and Shapiro-Schulz theorem. Now, we saw at the beginning that the equivalence between 3 and 2 can, in the scalar case, can be obtained assuming by using the positive answer of the Feichtinger conjecture. And so one natural question here is to ask whether multidimensional Feichtinger conjecture holds true for those model spaces. Namely, if you have a sequence of model spaces in H2, is it true that if it is a bessel system, then it can be partitioned into finally many RISC systems? But although Carlson's theorem extends in this multidimensional setting, this question has a negative answer, because we will see in a bit that if the dimensions of the subspaces are allowed to grow to be unbounded, then this is not true anymore. I think I don't have much time left, so I'll just keep this example and I'll go, well, actually, yeah, and I'll go right to the Feichtinger conjecture because I think it's a little bit more interesting. Okay, so how can we show that this multidimensional Feichtinger conjecture does not hold true? Well, pick a sequence Mn of sizes that is divergent, and choose two sequences of radii Rn and Sn that approach 1, and they're very close to each other pairs-wise. So basically, oh, that should be a sorry, this should be a Sn, so S of Sn. So basically, you're choosing 2 points, Rn and Sn, that whose zero hyperbolic distance essentially is very small. It's less than 1 over n. That's what this condition says. And then you choose M1 and Mn over 2, the binomial coefficients, equidistributed points on those two circles. Now, the picture here is where Mn is equal to 4, so Mn 4 over 2 is 6, and we have those 6 equidistributed points on those two circles. Now, the idea is that those two circles are very close to each other, and now we want to assign those 12 points, in this case, to 4 different matrices, A1 through A4, in this way, such that essentially each kernel at one of the, for example, here, one of the red points is close to each one of the other colors. That's why I chose these binomial coefficients here. And so in this way, for any n, you construct mn diagonal matrices of size mn minus 1. So here the role of mn here and mn minus 1 is switched. There was a typo. But the point is that since you have this, you constructed in this particular way, now the distance between any two of those model spaces is going to be small, because the distance of any two elements of their basis is. Because remember, H1, for example, is the linear span of the kernel at the red points, and so on. And this is true no matter how you choose Rn. And the idea now is that Mn is going to be a large number, so you're going to have a large cluster of those model spaces, which are very close to each other. And now you wiggle the parameter Rn, because you can actually prove that on the other hand, if Rn is going to one fast enough, then the sequence of model spaces that you obtain in this way is going to be a bessel system. But the previous slide is not going to be the disjoint union of finally many weakly separated sequences, and so he cannot be the disjoint union of finally many RISC systems. So that's the idea that goes kind of behind the argument. And the idea here is that we are using complex analysis tool really to understand a problem in operator theory, because we're using like those circles, the fact that those points are at a pseudo hyperbolic distance, very small to each other. And I think I'm a little bit out of time, so I apologize for that, and I thank you for your attention.
Okay, so thank you very much for this beautiful talk. So does anyone have any question or comment? Anything?
I have one question. So do you know if there is any maybe, so what you have shown is that if the dimensions are unbounded, then the Feichtinger conjecture falls. But maybe there is some kind of rate of growth. So how fast those dimensions grow? Maybe there is some kind of rate of growth of dimensions where the Feichtinger conjecture will still hold, or what do you think about?
So in this case, if you have Mn over 2, well, Mn can be any sequence that basically diverges, and Mn over 2 will be just Mn squared asymptotically, right? So I would say that if you have even the lim sup of the dimensions to be infinite, that's not gonna be possible. You're still gonna be able to construct something like that, probably.
With the very slow growth. Yeah, okay, that's what I wanted to know.
Probably yes, yeah. I would say yes now. But thank you for the question.
Okay, thanks.
Okay, so is there any other question?
Yes, I have a question. First of all, I'd like to thank the speaker for this very nice talk. I'd like to ask you, you know that the Carlson condition can be written in terms of a pseudo-hyperbolic distance. And do you think that your condition can also be written in terms of some distance in the Grassmannian of the Hardy space? Because in some sense, what you are taking are distances between subspaces. And
yes. Well, I'm not sure. I mean, so you're basically asking whether this bessel system condition for model spaces in H2 can have a more geometrical equivalent condition, correct? So what I suspect is that, you know, a model space is generated by a linear function. So it's like, let's say, in this case, H2, like the orthogonal complement of Bn times H2. So what I try to find is a function theoretical equivalent condition. So a conditions on the function beta Bn, sorry, those Blaschke factors in this case, that would be equivalent to being a bessel system, but I couldn't find one. There was some details that would not work. I mean, you can find it if they're all one-dimensional, of course, because it's just the Carlson measure condition. But I don't think, as far as I know, at least, there is no like really nice geometric condition that also takes into account multiplicities or the fact that each matrix packs a lot of eigenvalues, for example, inside it. So
Okay.
I think no, I mean, not yet, at least.
Okay. Thank you. Thank you very much.
Okay, so is there any other question or comments? Okay, so if not, let's thank the speaker again.